Please welcome to the virtual stage Mr. Michael Lydon, Senior Intelligence Officer at the Air Force Office of Special Investigations.
Hello, and welcome to the Overcoming Security Threats session. My name is Mike Lydon, and I am the Senior Intelligence Officer for the Department of Air Force Office of Special Investigations. We're an intentionally quiet organization, perhaps best known for inspiring the phrase Men in Black, or as the employer of the $6 million man. And as those associations might indicate, technology protection is a major priority for OSI because advanced technology is at the core of every Air and Space Force's mission. Consequently, I've been asked to provide context about the priorities and challenges facing microelectronics hardware security by my trusted colleagues and friend, Dr. Carl McCants, of which I'm very grateful. As an intelligence professional, it's not often that I get a chance to speak to such a wide and diverse audience. I'd like to open this talk by discussing hardware security threats in the context of renewed great power competition, because I believe those two are inseparable. This makes for an especially complex narrative that's going to bounce between strategic, tactical, and operational level implications, so it's doubly important to do a little baselining and scene setting. Great power competition is the central challenge to U.S. prosperity and security. A rapidly growing China, resurgent Russia, aim to coerce their regional neighbors, undermine long-standing alliances, and displace American influence from critical regions around the globe. Over the past several decades, the U.S. Air Force's space and Air Force's technology enterprise focused on developing technical advances to enhance operational effectiveness. The goal was to confer an unprecedented force multiplier to our advantage so that we could do more with less. However, the Air Force is now operating in a changed strategic environment. The globalization of technology now allows potential adversaries access to cutting-edge science and tech research and the best science and tech talent. As they work toward reaching technological parity, they also push to erode our military's technological superiority. Our adversaries perceive the U.S. as having reached a point of irrevocable decline. It doesn't matter if you agree with that assessment, that is irrelevant. What matters is that our adversaries, and likely some of our allies too, believe it. This belief structure makes the world a far more dangerous place because it emboldens our adversaries to behave in ways they wouldn't have before. For example, let's look at the definition of economic warfare. The use of, or threat to use, economic means against a country in order to weaken its economy and thereby reduce its political and military power. While I'm certain smart people will disagree about the technical definition or label of economic warfare, I do think that most of us will at least see the warnings of economic conflict with the People's Republic of China. There's little question that, for over a decade, Beijing has engaged in a sustained campaign of cyber-enabled economic aggression against us and our allies. They have targeted our most productive economic sectors, including semiconductors, telecoms, advanced computing, robotics, energy generation, resource extraction, aerospace, the medical sciences, just to name a few. We are currently facing off with China on 5G technology, machine learning, quantum computing, nuclear and solar power, satellites, rare earth elements, biotech, pharmaceuticals. Fundamental to this Chinese strategy for winning in each of these areas, and many more, is the rampant theft of American intellectual property. This is why economic security is national security. To quote General Keith Alexander, now retired, the former director of the NSA and founding commander of the U.S. Cybercom, the Chinese playbook is deceptively simple. Why spend trillions of dollars on basic science or advanced research when it can be stolen with almost no penalties? The Chinese government is stunningly good at this theft. Not only do they employ thousands of government operatives to engage in this effort, a new federal indictment charged that they have been fostering a criminal network, a criminal hacker class that works for its personal economic gain as well as for the Chinese state. All of this intelligence and economic activity is directed at one key goal: to replace the United States as a global leader. Make no mistake, This is the backdrop for all of our work in hardware security. While production shortages, trade disruptions, natural disasters, and other unforeseen events can all stress America's global supply chains, actions by foreign adversaries to exploit vulnerabilities in U.S. supply chains pose unique counterintelligence and security threats. Foreign adversaries are increasingly using companies and trusted suppliers as attack vectors against us for espionage, information theft, and sabotage. In doing so, they are compromising the products and services that underpin America's government and industry, resulting in lost IP, jobs, economic advantage, and reduced military strength. Over the past decade, for example, state-sponsored hackers have compromised software and information tech service supply chains to steal IP, conduct espionage, and carry out sabotage. With the recent SolarWinds compromise, that has brought greater public attention to software supply chain attacks. It is also the latest in a long line of such attacks in recent years. Increased risk to supply chains are due to evolving dependence on globally sourced commercial technologies for mission-critical systems and services. Resulting residual risks are passed to end-user enterprises in the form of products and services that may contain defective, counterfeit, or otherwise tainted components with Trojans, malware, exploitable weaknesses, and vulnerabilities from sources with unknown trust. An evolution of that traditional risk equation is required to address risk topics relevant to the reliance on others who make risk decisions about matters in which they are not the risk owners. In the past, business leaders viewed risk management as a balancing act between cost, schedule, and performance. But the risk landscape is constantly evolving, which demands that the evaluation and management of those risks are adjusted accordingly. Security is just such an instance. With the rapid rise of asymmetric threats and constant attacks to computers and networks worldwide, security must be added as a fourth pillar of the risk equation with equal emphasis to cost, schedule, and performance. To more deeply understand and justify performance and security risks as an imperative, it is necessary to consider the functions of threat, vulnerability, and consequence, and their calculated risk impact. From the threat perspective, an understanding of the adversary's intentions and capabilities is vital. Key to this is using the latest threat information to determine if specific and credible evidence suggests an item or service might be targeted by adversaries. But it must be noted that while adversaries wish to do harm, they can also be successful if systems, processes, services, whatever, are vulnerable to attacks. Vulnerabilities are weaknesses that are either inherent to the system or have been introduced into a system by an outside agent. Lastly, the consequence of the risk must be considered. If the threat is realized and the system is attacked and or compromised, the outcome is either fixable or fatal. So under this construct, a supply chain risk is when the capability and intention of an adversary aligns with the opportunity to exploit a vulnerability. The consequence of this would be would allow the adversary to extract intellectual property, sensitive or proprietary data, etc. Furthermore, such an action may allow an adversary to surveil, deny, disrupt, or otherwise degrade a component, a system, or service. These actions may compromise the integrity, trustworthiness, and authenticity of critical microelectronics. So as background, let's talk about the critical challenges that we face when deciding how to secure our trusted microelectronics hardware. In all cases for attacks to occur, there must be an opportunity for the adversary's capabilities to be applied at any point in the supply chain lifecycle, from concept to design, manufacture, integration, deployment, maintenance, and retirement. The threat can be realized when an adversary's capabilities and intentions align with the inherent or introduced vulnerabilities of the system. There is no certainty that an attack will happen, but risk is realized when this alignment occurs. For example, in the manufacturing phase, there may be poor programming processes that permit the use of software from an unwitting, non-trusted third party that has been compromised by a bad actor. Or in the maintenance phase, there may be poor standard operating procedures that permit a maintenance technician to enter and roam free in a facility unsupervised. Scenarios such as these illustrate that often there is a reliance on others to make decisions about matters where they are not the risk owners. thus allowing unknown or misunderstood residual risk to be passed to end users, program systems, and even entire organizations. Okay, so this is the point where we need to red team this out. Let's take everything we've talked about thus far and think about it from an adversarial perspective. In order to do that, you have to think about the effect you want to create. The effect derives the kind of operational construct you choose. However, the more complex the attack, the least likely it is to succeed, let alone be green-lighted for operational success. Operational planners consider many variables, including resource and time requirements, likelihood of assessed attribution, likelihood of getting caught, ramifications of getting caught, and potential unintended consequences. This means that the bad guy will look to identify which vulnerabilities most closely align with their capabilities, all with an eye on their own risk tolerance and the variables I just discussed. So with that in mind, IP theft can be an indicator of something much more sinister than an attempt to clone a chip for economic gain alone. It can be an indicator that an adversary needs that IP to develop or refine its technical capability to sabotage, subvert, or exploit the system that microchip is destined for. With that in mind, let's revisit the supply chain risk model and look at what phases are most vulnerable to an actual real-world attack. Thinking like this virtually eliminates the James Bondian scenario of men in black turtlenecks and balaclavas fast roping out of a helicopter onto the roof of a Taiwanese fab. So let's move the conversation away from the realm of possible, past even plausible, and let's talk about what's probable. And honestly, and in my assessment, thinking this way makes supply chain attacks at the fab or assembly or test phases very difficult to pull off. But it also illuminates other windows left a crack open. Assuming that enabling IP theft has already taken place via cyber exfil, insider threat, reverse engineering, what have you, the risks I've highlighted in red here fall into a sweet spot for adversarial supply chain operations, generally easier to subvert, sabotage, or exploit with less quality assurance processes in place. Of all the various threat vectors, I'm by far and away the most worried about maliciously modified clones, fabricated overseas and inserted into our supply chains, most likely through the gray market. Why go through the trouble of subverting an incredibly complex fab when you could make the part in the safety and security of your own government-owned and operated facility? On the list of what else keeps me up at night, this is closely followed by an adversary subverting third-party intellectual property cores used in ASIC and system-on-a-chip designs, as well as in the programming of programmable logic devices. Are we actually vetting the pedigrees of those designs or codes? On that topic, who is actually loading your bit streams onto your FPGAs, for example? Have you outsourced that to the chip vendor? That seems like a very exploitable process to someone like myself. I worry about the exploitation of design environments and software, of course. And from a sabotage perspective, I worry about 5G-enabled machine-to-machine communications. A simple overlay of countries with agreements with China's Huawei for 5G infrastructure and where we fab, test, and assemble semiconductors, right? There's a significant overlap there, and that scares me. But there are different levels of disruption, which I'll talk about here. And while we've covered some that fall in the realm of intelligence-enabled operations, we can't ignore the effects of some of the larger economic and national security threats, because how we respond to those affects the kinds of operational attacks that our adversaries have at their disposal to leverage. So let's look at some of those macro trends and see how they could affect our adversarial operations. Whether or not you agree humans are the cause of climate crisis is irrelevant, as we have to deal with the effects regardless. So for example, record droughts in Taiwan, combined with a pandemic and a highly concentrated and consolidated industry, highlight choke points and limitations of the global microchip supply chain, and suppliers cannot keep up with the current demand for microelectronics. A fragile system is more vulnerable to disruptions like adversary-backed exploitation, subversion, or sabotage, and supply chain disruptions increase risk tolerance, which incentivizes shortcuts. Shortcuts are even more vulnerable to exploitation. So until a more diversified collection of trusted domestic and international partners can match demand, the DoD suppliers may need to turn to the gray market to fulfill orders with resources confident which reduces confidence in authenticity, increases the risk of counterfeits or malicious modifications, and the potential for outright failures of DoD and Department of Air Force systems. As an example of this scenario, I'd like to combine all the elements I've spoken about so far in a single risk example: likely threat vectors, our own acknowledged vulnerabilities, and the resultant consequences. It's not exactly a state secret that the DoD's weapon systems tend to have rather long shelf lives. Let's look at the F-22, for example. In 1981, the Air Force identified a requirement for an advanced tactical fighter to replace the F-15 and F-16, codenamed Senior Sky at the time. The RFP was later issued in 1985, a prototype was first flown in 1990, and the first F-22 production model was unveiled in April of 97, with its first flight in September of that same year, just over 24 years ago. Clearly, the timelines of these kinds of R&D and manufacturing is very different than, say, for the latest iPhone. As a result, the DoD uses a lot of old microchips. And where do we get them? Well, after years of looking, I can confidently say that there is not a secure warehouse in central Missouri full of obsolete microchips sitting in climate-controlled storage, waiting for the DoD to purchase them one or two at a time. No, we turn to the gray market, which is dominated by China-based suppliers who in part rely on recycled e-waste to resupply us. We've all seen the pictures of little kids melting the solder off of PCBs over open fires. Those are the chips that end up back in our weapon systems. Now consider all the IP theft I talked about earlier, and add to that the fact Chinese companies have purchased a lot of the original manufacturing equipment on the secondary market. Add to that academic research into hardware Trojans. Add to that great power competition, and we have a real problem on our hands. Or maybe even all that is too complicated and risky for our adversaries. Maybe the real threat is simply supply reduction, simply shutting off the spigot of the obsolete and counterfeit chips so very necessary for our sustainment of our own systems would have rippling effects throughout our readiness levels. So how do we mitigate this? Does reshoring really offer a solution? Well, spoiler alert, expanding advanced manufacturing domestically doesn't solve our current requirement for trusted, obsolete microelectronics. But clearly it has a positive implication from an economic and national security perspective. And I don't think I need to belabor those points. However, I would like to raise one potential unintended consequence. There is a scenario where great powers try and untangle key sectors of their economies, and this leads to new levels of IP theft and technology-related corporate-focused espionage. This isn't an official intelligence forecast. This is simply deductive reasoning and common sense. Split economies in a bipolar world generate increased competition for the remaining countries' businesses. Competition drives espionage. Additionally, the scenario is complicated by the theory, which I prescribe to, that free market systems are more vulnerable to manipulation by centrally managed, closed systems in global competitions. The winner isn't always the one who plays fair. So, then how do we improve our odds under the veil of unfair economic competition and state-sponsored corporate espionage? We recognize that the DoD and commercial industry interests are largely aligned, and we face the same reality. The DoD needs to recognize it's a challenging customer and evolve its acquisition processes to meet the challenges of an economically intertwined great power competition in a digital age. The risk of adversarial supply chain operations are real. Industry needs to accept that it can't fully secure itself completely against a nation-state actor by itself. And finally, the world is complicated, and so are the threats. We can't ignore emerging threat vectors like adversary-backed venture capital, tech incubators, and startup competitions attempting to exploit our innovation base, especially as we shore up traditional defenses against cyber attacks and insider threats. So, we need to build mutual trust in one another through active listening, value-added dialogue, information sharing, cooperative security, and judicious application of security and counterintelligence resources. We need to expand our aperture for partnership beyond the traditional DIB in recognition of DoD's embrace of commercial innovation. In order to effectively counter threats, mitigate vulnerabilities, and actually understand the consequences of our actions or inactions. We must stand in solidarity to protect our IP and our economy. The DoD and industry both need to do a better job collecting and sharing actionable threat intelligence and actively collaborate to protect each other through collective defense. And only then can we ensure the sanctity of our IP and have confidence in the integrity of our microelectronics supply chain. Thank you for listening and enjoy the rest of the day. Take care.
And now, for a discussion on detecting hidden Trojans in FPGA applications, DARPA MTO Program Manager Mr. Keith Rebello and Dr. Angelos Karamidis, President of Ether Argus.
Hi, I'm Keith Rebello. In October of 2018, Bloomberg Businessweek published a headline-grabbing article describing cyber attacks originating in the hardware supply chain. While the attacks described in the article remain unconfirmed, the article did bring attention to a plausible and largely overlooked security threat that the United States relies heavily on commercial, off-the-shelf electronic assemblies, most of which are produced overseas. Small changes to those assemblies could lead to complete compromise of the systems that use them, highlighting that security is not just the problem of software networks. It also requires ensuring the integrity of system hardware produced by a complex and highly distributed supply chain. The challenge with detecting malicious behavior in state-of-the-art assemblies is their enormous complexity. For example, the hardware platform for a modern server includes a motherboard with thousands of components. It includes multiple CPUs with multiple cores, each capable of executing multiple threads. It might include GPUs or hardware accelerators. It includes controllers for memory, disk I/O, and network interfaces. It might include a baseboard management controller for remote system administration and a trusted platform module to support secure boot and remote attestation. This hardware platform supports a software stack that might run multiple virtual machines, each running thousands of processes. And the server could be located in a data center with hundreds or thousands of other servers. Is it even possible to detect malicious activity against such a complex background? The Safeguards Against Hidden Effects and Anomalous Trojans in Hardware, or SHEATH, Microelectronics Exploration Program, was devised to address this fundamental question. Over 18 months, performers were challenged to build representative hardware Trojans for complex systems and to develop detection techniques that allow identification of Trojan behavior in noisy environments. The approaches used by the SHEATH performers include techniques for isolating components or peripherals from sources of noise, using targeted stimulation and probing to amplify signatures of Trojan activity, and employing machine learning-based anomaly detection algorithms to pick out very weak signatures. The example Trojans developed for SHEATH covered a wide range of system behaviors and insertion points. Performers developed multiple man-in-the-middle Trojans for various peripheral interfaces. A trusted platform module interposer could disrupt TPM operation or compromise the transmission of random numbers generated by the TPM. An interposer on a baseboard management controller interface modified system administration actions. A man-in-the-middle Trojan on an Ethernet interface allowed tampering with network traffic. And a keylogger on a USB interface recorded user keystrokes. A malicious network interface card on a server's PCIe bus used direct memory access to arbitrarily read and modify system memory. And a Trojan inserted in an FPGA-based accelerator produced targeted misclassification of results from a computer vision algorithm. These Trojans and the complex systems that contain them provided a realistic testbed for the SHEATH detection approaches. SHEATH set ambitious goals for detection, accuracy, latency, performance impact, and system complexity. Multiple SHEATH performers demonstrated viable approaches with some possible trade-offs between detection accuracy and latency. We are pleased to bring demonstrations of 3 of these approaches to ERI. Assured Information Services will be demonstrating their Falchion approach, which uses hypervisor-based peripheral isolation to reduce the noise produced by normal peripheral interactions and to provide a platform for peripheral probing and monitoring. SRI International will be demonstrating their Orchest approach, which uses intelligent probing to reveal the presence of Trojans. And Ether Argus will be demonstrating Tempest, which uses electromagnetic emissions to continually monitor system operation. Ether Argus will also be providing a detailed overview of their approach now on the ERI main stage. I'll turn it over to Angelos Karamides to tell you about Tempest. Angelos?
Thank you, Keith, and thank you everyone for attending this talk. My name is Angelos Karamides, and I am the president and co-founder of Ether Argus Incorporated. Today, I will talk to you about our work during the DARPA Sheath program that Keith ran. Our project, named Tempest, focused on the detection of hidden Trojans in Fpga applications using Fpga-accelerated artificial intelligence applied to object recognition as a motivating application. First, a few words about Ether Argus. We are a small startup co-founded by faculty members from Georgia Tech and Virginia Tech. Our goal is to commercialize and transition technologies related to electromagnetic side channel-based security that were developed with government sponsorship, including the Sheath program. The general idea is to use the unintended electromagnetic emissions that are generated as a natural byproduct of the operation of an electronic device to be able to say something about the current state of that device. I should point out that we are not looking at intended electromagnetic emissions such as Wi-Fi, cellular, or Bluetooth radio traffic. The purpose of our technology is to help defenders confirm the integrity of the hardware and the software of the devices that they care about without deploying new software on those devices. This has applications both for what we call real-time attestation, that is the continuous security monitoring of critical devices, and on supply chain security. With that in mind, the goal of our work in the Sheath program was to develop non-intrusive technologies for identifying malicious Trojans that have been inserted in the firmware of embedded devices. While our techniques would also identify certain types of hardware modifications, such as the ones Keith referenced earlier, for demonstration purposes, we focused on the lowest level of the software stack, frequently referred to as firmware. Trojans inserted at those levels are very hard to identify and counter due to a lack of effective tools and the constraints imposed by limited resources and access difficulties at such low levels of the software stack. This kind of Trojan insertion would typically happen during a supply chain attack, similar in nature to the SolarWinds compromise we saw earlier this year. Except that an attack through the firmware would be even harder to identify and remediate. So as part of Sheath, we worked to first demonstrate the feasibility of our techniques in a 6-month sprint, and to then further explore, refine, and demonstrate them in the context of a real system and application. I will show you a brief recording of that demo later in this talk. But before we get to the demonstration, let me briefly outline the general idea behind our approach. The high-level concept as shown in the graphic in this slide is relatively straightforward. We take one instance or a small number of instances of the device that we are interested in protecting. We then operate this device as a normal user while recording unintended electromagnetic emissions generated during its operation. These emissions represent a complex signature of device behavior that represents the interaction of specific software instructions executing on the specific hardware of the device. As the device executes different instructions, these emissions change over time. If the software is changed, then these emissions would also change, sometimes in subtle, sometimes in very obvious ways. If the hardware of the device changes, these emissions would again change, typically in much more dramatic ways. So using these emissions, we then construct a model of device behavior as seen from the electromagnetic spectrum. This model can then be used to monitor all instances of that device during operation, even instances that we have not previously had a chance to build a model for. It is important to note again that we only need one or a small number of sample devices to develop the monitoring model, but we can apply that model to all instances of that device. So again, we do not need to train on all the devices we may be interested in protecting. So now, if during monitoring the device is different from what the model indicates, and the difference could be in terms of software it executes or the hardware it is composed of, then our system can identify that difference based on the emissions seen in the electromagnetic spectrum and notify the operator or take some other pre-programmed action. Such monitoring can be done when the device is first received for testing, or that is prior to its deployment and use in the field, or it could be done periodically during system operation, kind of on a sampling basis, or it could even be done continuously for high-level, high-value devices, or any combination of the above, depending on the risk profile and operational considerations. Now, to motivate and test our approach, we used data center grade field programmable gate arrays, or FPGAs. I will say that, however, nothing in our approach is particularly specific to FPGAs. We just use the FPGAs for ease of demonstration. I will say a few words about other devices that we applied our approach to during Sheath toward the end of the talk. Now, FPGAs in general are used for a wide variety of performance critical tasks. And one such task is AI, that is artificial intelligence enabled vision applications, such as object recognition in real-time video streams. These FPGA boards are very well suited for these tasks, and a number of commercial and open source applications and application frameworks exist for allowing users to build their own object recognition applications. So what you see here in this slide is the experimental testbed that we used in Sheath. Namely, you see a rack-mounted server with one or more FPGA boards that are running the object recognition application. Now, near it, we have placed a software-defined radio with a near-field probe, which we use to do the electromagnetic spectrum sensing. And the software-defined radio is connected to a laptop that, for the purposes of our research, is acting as both the training and the monitoring station. So the goal for the project was to demonstrate the techniques that I mentioned earlier with system prototyping to address swap factors left for future work. So in this environment, in this setup, the goal of an attacker would be to insert a Trojan in the logic that is executed on the FPGA, interfering with the object recognition application without being detected. Now, the logic we ran on the FPGA boards was based on the PipeCNN open source image analysis framework. The board was programmed to look at a stream of images, identify airplanes in them, and then produce an annotation as to whether the images represented a commercial airliner or a military jet. So what you see here is an example output from the application. So for each of these images, the system adds an annotation on the upper left corner indicating whether the image contains an airliner or a warplane based on the execution of the AI framework. Now, purely for the purposes of demonstration, we also added a second annotation to indicate whether that inference, whether it's an airliner or warplane that the AI made, was correct or not. So on the left, you see the output from the unmodified application where all the inferences are correct. On the right, you see the output from the application where a Trojan has been inserted. And this particular Trojan causes the system to misidentify a specific jet, military jet, under certain conditions. Now, zooming in, here is one of the warplanes that on the left, with the unmodified, untampered application, was classified correctly as a warplane. But on the right, the Trojan has caused this to be misclassified as an airliner because the Trojan changed the output. But all the other airplanes that I showed you were classified correctly. Now, we implemented a few versions of this Trojan to experiment with different placement, different size, and so on. On average, the addition of a Trojan represented a change of between 1 and 3% in terms of the code executing on the FPGA relative to the original application. Now, before I show you the results, let me say a few words about the technical approach we used. Fundamentally, we use a supervised machine learning algorithm applied to the select features extracted from the electromagnetic signals that the FPGA board, in this case, emitted during its operation. Now, the models we generate in this way can be used in two different types of detection during inference. Runtime detection identifies deviations from that model that correspond to the Trojan being activated and executing. Structural detection, on the other hand, identifies emissions that are caused by a Trojan that is present in the FPGA, in the bit stream, but is inactive. So as you can imagine, the latter is much more powerful in terms of a detection primitive, but it's also much harder to achieve. So without further ado, here's the summary of our results. What you see in the table on the top of the slide is the accuracy, recall, and false positive, false negative rates for runtime detection of 3 Trojan variants labeled V1, V2, and V3. These 3 variants all achieved the same goal that I showed you in the previous slide, 2 slides ago, which was to misclassify a specific warplane under certain conditions, but they were implemented differently and affected different parts of the AI application itself. Now, at the bottom of the slide, you see a visual depiction of the relevant part of these electromagnetic spectrum emissions when each of these Trojans is activated, as well as on the electromagnetic spectrum when the unmodified application is executing all the way on the left. So, as you can see from the results in our table, our ability to correctly identify the presence of unknown logic, the Trojan in this case, is very good. And note that we are not detecting the presence of any specific signature or any specific Trojan, but rather we are looking for a difference from the behavior of the clean model. So this means that we are not tied to these 3 Trojans, but really any kind of Trojan or other modification to the FPGA logic. Now, the column on the table labeled V3-extra work represents a Trojan that is somewhat larger in size than is necessary to achieve the goal that I talked about already. So as you can see, a larger Trojan appears to be easier to detect, which is also intuitive. Now, the final column on the table, labeled V3-inactive, illustrates our ability to do structural detection, that is, identify the presence of a Trojan even when that Trojan is not activated. Now, in all these cases, detection happens within 1 second of the Trojan activating, or for the case of the inactive Trojan detection or structural detection, within 1 second after the object recognition application itself begins executing. So let me briefly show you now what this all looks like with a brief 2-minute pre-recorded video.
Here is our setup. First, we have a Dell R815 server. This server connects to the accelerator over a PCIe connection. Additionally, the server acts as a host computer, rapidly sending images of airliners and military jets to the accelerator and requesting their classification. In this demonstration, we have an unmodified version of PipeCNN running on the FPGA. Once the image has been classified by the accelerator, it is sent back to the host and then displayed on the left monitor. The top text on the displayed images denotes what the accelerator classified the image as. For demonstration purposes, the bottom text denotes whether this is the correct classification or not. Our algorithm continually samples the signals being emanated from the FPGA and compares these to training signals that we have previously recorded. If a deviation in the signals occurs that is larger than normal variance, our algorithm will alert that an anomaly has been detected. But in this case, since no malicious Trojan is running within PipeCNN, our algorithm continually monitors the device. Now let's do the demonstration again with a small Trojan hidden in PipeCNN that intentionally misidentifies the Iranian fighter jet as an airliner. Note that since the images are displayed to the left monitor after all processing on the FPGA has been completed, our algorithm will detect the anomaly slightly before the image is actually displayed. Without knowledge of what frequency components the Trojan will activate, our algorithm is still able to detect the Trojan. A window with the text "Anomaly Detected" appears on the laptop to warn that a malicious attack may have occurred.
Now, in addition to baseline performance, we also looked at other factors that might affect our approach when deployed in the real world. For example, we looked at whether multiple FPGA boards in close physical proximity would negatively impact detection. Now, such a scenario might be encountered in a data center or cloud environment where each server has a few such boards plugged in. We experimented with exactly such a scenario, and as you can see from our results, which used the V3 extra for demonstration, there is no impact to our detection ability. As I mentioned earlier, FPGAs were the device that we settled on to demonstrate our approach. But as part of our work, we looked at numerous other devices of various kinds, some of which I'm showing on this slide. Although we did a deep dive on FPGAs, we have confirmed that our approach applies with some small variations to all of these devices. For all of these, we have been able to confirm device and firmware integrity during the boot sequence and on several cases to detect runtime attacks, all without modifying the devices. In fact, in most cases, we do not even need to open up the device enclosure. So at the end of the day, what the concrete outcome of our 18-month sheath effort is an initial ability for verifying the integrity of bit streams executing on FPGA boards that can be applied during different phases of system lifecycle or operation. A secondary application is to use the same technology to identify what bit stream, or more generally, what version or instance of firmware is executing within a device without having to trust self-reporting by that device. Of course, an 18-month effort can only scratch the surface here. There are several opportunities for additional research. Perhaps the most obvious has to do with whole server assurance. In our project, we only addressed one type of embedded device within a server, the FPGAs, but one can easily imagine extending this scheme to cover most or even all relevant server components or expansion boards. Another possible direction would be to look at the limits of our techniques. What can we do with higher complexity systems? And another intriguing opportunity is to look at ways to design or compile firmware or software so that we can achieve even better detection if we assume that our approach is present and monitoring. So in summary, our work in the sheath program explored and demonstrated the possibility of identifying firmware Trojans via unintended electromagnetic emissions. Through this effort, we were able to rapidly prototype and validate an initial capability for identifying Trojanized FPGA logic. We were further able to explore the general applicability of the approach to a large variety of other devices, leaving deeper dives to these for future work. We are currently exploring other applications of our approach in a variety of environments, including 5G deployments and data center environments. Thank you for your attention.
Returning to the stage, DARPA MTO Program Manager, Mr. Serge Leaf, joined by Ms. Deidre Hanford, Chief Security Officer at Synopsys, to discuss holistic semiconductor security.
Hello, my name is Serge Leaf, and I'm a Program Manager at DARPA's MTO office. Today, I will talk briefly about holistic semiconductor security. The problem that we decided to address here in MTO is that many of today's chips are intrinsically insecure because it's really complicated to design, and the economics of incorporating security into design is very complex. Thus, we put together a program called ACE. The vision of ACE is that tools, methodologies, and IP would be created that would enable dramatic improvements in SoC security. The program consists of three prongs. First prong is security tools that enable engineers to design chips that are intrinsically more secure. And the elements of security tools that we're addressing are obfuscation, watermarking, simulation of attacks, and analysis of threats within the design. The second prong in this program is the on-chip security prong. In other words, what sort of mechanisms can and should we put into the architecture and microarchitecture of SoCs and ASICs to enable the chip to actively participate in securing their operation. Some of the capabilities that belong here are authentication, provisioning, monitoring, enrollment, and enforcement of security policies. Lastly, a third prong is about integration. And integration has to do with weaving the security structures into the architecture of the design. And that means that we need to be able to automatically or semi-automatically implement platforms that incorporate security mechanisms right into the architecture of the SoCs. And this implies creation of platforms, automatic generation of IP and platforms, synthesis of interconnect, and optimization of the entire design. So synthesis of secure chips is an interesting topic. In fact, synthesis at the chip level is a problem that has not really been solved by EDA industry in the course of the last 30 years. At best, the state of the art is to synthesize one block at a time. In ACE, we're looking to synthesize and optimize an entire SoC. Historically, this synthesis and optimization was based on exploring trade-offs between performance and size of the design. But in modern chips, it is increasingly important that power also needs to be considered when assessing these trade-offs. And even more recently, it became apparent that security also needs to be viewed as one of the elements that would be used to assess the goodness of the overall design. And security is not a single thing. Security actually, per our definition in MTO, consists of defenses against the 4 specific attack surfaces: side channel attacks, supply chain attacks, reverse engineering, and malicious hardware. And what that implies is that what we really need to do is we need to be able to optimize systems on those multiple axes of optimization. This brings to the table interesting challenges. One is, how do you quantify security? That the notion of security quantification is not particularly well understood. The other is, how do you rapidly estimate resistivity of a particular architecture to an attack? And lastly, how do you actually optimize a chip in 7 dimensions when current state of the art is between 2 and 3? So in the context of the ACE program, we decided that the central element of all of this is something called security engine, which is an on-chip piece of IP that incorporates different degrees of defenses against the 4 attack surfaces that I had mentioned earlier. This security engines are modular, and they have hardware and software elements. And in the course of the ACE program, we've had 3 such things implemented. One is based on ARM CPU, one is based on ARC, and one is based on RISC-V. Each of those security engines has different attributes and different capabilities in addition to a lot of common objectives that are implemented. For example, the RISC-V one that's being done by Northrop Grumman has some specific features that are unique to the expected requirements of the defense industrial base. All of these security engines can be configured based on optimization of performance, area, speed, and security constraints. And all of this are intended to be field upgradable through security policies. In general, a security engine would sit in an SoC as shown in this diagram, and it would contain a hardware root of trust, identity, configuration keys, certificates, status meters, and many other things. And this security engine can then be used to enable or disable different pieces of IP, and in fact obfuscate and deobfuscate parts of IP to offer defenses against attacks on all 4 surfaces mentioned earlier. And existence of something like this would enable an entire chain of capabilities. For example, during the design time, you can create a secure SoC by incorporating this type of security engine with inborn root of trust. During different stages of manufacturing, you can enroll the unique identity of each die. You can configure it during package testing. You can provision it while it's at system OEM. You can personalize it, authorize it, and update it and monitor it during its life in the field. And so ACE as a program started about a year and a half ago. And the goals were to, through automation, significantly reduce design time. And in ACE Phase 1, and the goal to design medium complexity SoC is about 3 months. And in Phase 2, it'll be 1 month. And in Phase 3, it'll be 1 week. And if you follow the security engine capabilities, its security engine starts as a static piece of IP, turns into a generator, and finally becomes an optimized entity where the capabilities of defenses on multiple surfaces are traded off against chip economics. And similarly, capabilities within the security engine evolve over time. And so ultimately, what happens is from each of the phases of ACE comes out implementation view of the design, which can subsequently be driven into the implementation methodologies and tools that the designers normally use to go from logical to physical representation of their design. We have 2 incredible teams working on this program. One team is led by Synopsys, and it has ARM, University of Florida, UC San Diego, and Ultrasoc on that team. And the second team is led by Northrop Grumman, and they are partnering with IBM, University of Florida, and University of Arkansas. Thank you for listening. My presentation will be followed by more details from Synopsys.
Thank you so much, Serge. I'd like to thank Serge Leaf and Dr. Mark Rosker for the invitation to speak at ERI and to represent Team ACE. Today I have an opportunity to introduce you to ACE, which stands for Automated Implementation of Secure Silicon. We've just wrapped up our first year of performance on this DARPA program under Team Search. Today I'll talk about how we're elevating design for security to be a first-order design consideration, along with power, speed, and area. The benefit is that everyday designers can produce secure designs without having to be an expert in security. Hence our title today, Democratizing Secure Silicon. Our aim is to make designing secure silicon broadly accessible. I'm going to be covering 4 topics today. I'll speak to drivers for security. I'll introduce you to ACE and our team. I'll share our accomplishments in year 1, and we'll talk about what's coming next. So let's get started. Hardware attacks are on the rise. I'm happy to see the leadership that DARPA has in the security area with programs like ACE and other programs like Sith. In August, I watched a speech at the Hot Chips conference regarding the accomplishments of the Sith team called Morpheus. They're out of the University of Michigan. The resilience of that processor is really amazing. Certainly our warfighters and critical infrastructure applications require secure software and secure hardware. Compromises to these systems can be extremely serious. But really, consumers and enterprises also can be victims of hardware compromises. One team, shown here, was able to break into a company's network using a stolen laptop, despite all the security mitigations that laptop had, like a fully encrypted SSD using BitLocker and a fully secured boot mechanism. On the other example, earlier this year, a group of researchers from France were able to hack into 2-factor authentication keys using a side channel attack. So as a design community, we can't leave secure design only to applications like defense and critical infrastructure. We need to make design for security broadly available. ERI has a number of key focus areas that are being explored through this conference. Each of these areas have high impact. Heterogeneous integration is an area of great advancement right now, and one where DARPA and DoD at large are making investments along with the commercial industry. Of course, leveraging AI at the edge is an area where we can leap ahead and further enable the warfighter, as well as consumers and enterprise applications. So these 6 ERI initiative areas really set a framework for innovation that serve our national interests. On the top left of the slide is the focus area that our team's working on, overcoming security threats across the entire hardware lifecycle. Our goal on ACE is to enable the design of secure SoCs by creating an extensible and automated flow. That flow allows designers to trade off power, area, speed, and security, and to enable the mitigation of security threats. This will also allow for in-field provisioning in a secure manner. Now that we've covered the industry and DARPA drivers for security, let me introduce you to ACE and to our ACE team. As I've mentioned, ACE enables the inclusion of security in a design, and it's creating a threat-resistant design for designers who are not necessarily those design for security experts. Moreover, ACE enables different levels of security, arming designers with choice. Designers are very familiar with trade-offs between power, area, and speed, but with ACE, we introduce a fourth knob, one for security. So our mission is to make hardware designs more resilient to modern-day security threats. A baseline SoC, as you can see here, will be updated to a secure one. Keep in mind, there's really no one security problem. Security concerns differ based on the application and the priority of security against those other design parameters. So for example, what security do you need for a drone? Well, a chip inside a consumer drone may have very different security objectives than an autonomous drone deployed on a battlefield. While both may have power and performance requirements, the security objectives, I believe, would be measurably different. So really, security must be tunable in strength against very specific threats, such as untrusted supply chain, reverse engineering, side channel attacks, and malicious implants. And those really need to be prioritized against those power, speed, and area considerations. So our ACE approach permits the designer to trade off these 4 design parameters as appropriate to the application needs. So when we're done with the ACE program, the goal is that the flow itself, not the designer, will provide much of the security expertise. This enables composition of a security-hardened design, meeting security intent within bounds of the other design parameters. So what's the implication? For years, the electronic design industry has helped move designs up to a higher and higher level of abstraction. And then new design challenges come along. So for instance, when designs became more mobile, a lot of folks wanted to quickly figure out how to design for low power, but they didn't necessarily know how to do that low power design. So the EDA industry answered with automation, giving design teams a host of choices for design for low power, things like isolating and shutting down voltage islands, minimizing switching logic to avoid dynamic power, enabling multi-threshold gates, and even supporting some exotic capabilities like DVFS, dynamic voltage frequency scaling. Now we're going to do this again for security, delivering application-appropriate attack resistance and giving a spectrum of choice in security mitigations. So let me introduce you to the ACE team. First of all, we have Synopsys performers spanning 3 of our business units. But outside Synopsys, we have industry partners like ARM and Siemens, our defense industrial base partner, Boeing, and university researchers from Florida Institute of Cybersecurity. The UC San Diego team also includes Purdue University, and the Texas A&M team includes New York University and University of Texas at Dallas. The diverse perspectives represented here truly enhance our solution. Let me introduce you to Dr. Mark Taranopour from the Florida Institute of Cybersecurity Research, who will share his perspectives on our ACE team.
Thank you, Deirdre, for the opportunity to address the ERI audience. The team from the Florida Institute for Cybersecurity Research is proud to be part of the ACE program. The close collaboration between industry, government, and academia is an invaluable experience for all faculty and students involved. In fact, Synopsys and FIX are working together to secure SoC designs throughout semiconductor lifecycle, develop a security engine, security IPs, and watermarking solutions, establish innovative threat heuristics, deliver measurable and accurate security metrics, and enable in-foundry and in-field chip personalization and provisioning. The innovation and breakthrough made during this project have great chance to be deployed to the field through close collaboration with Synopsys as a leading semiconductor EDA company.
Thank you, Dr. Taranopour. Now that you've met our team, I'd like to share some of our Phase 1 accomplishments. As I've mentioned, we've completed our first year of this 4-year program. Well, first and foremost, this year we had to work out to architect our solution. With so many performers on our team, we really needed to devise a system where all the team members can be productive and contribute their part. Here we have ACE on one slide, and let me break it down for you. It's kind of complicated. At the top, you see an IP library. This library contains IP blocks including 3 diverse security engines. In addition to security engines from ARM and Synopsys, you also see a Northrop Grumman security engine. As Serge mentioned in his introductory remarks, Northrop Grumman is leading the other ACE team, and their RISC-V-based security engine may also be selected from our system. Powered by the IP library, designers may perform architectural exploration and SoC construction, and generate security directives for downstream tools. This is enabled using a security-enhanced version of Synopsys Platform Architect. So in addition to trading off power, area, and speed, designers can also tackle various security threats like supply chain, side channel attacks, malicious implants, and so on. The bottom half of the slide flows left to right. It represents the implementation path. Notice that this is where different security mitigations are introduced into the actual design. Completed designs are later provisioned with security keys and other secure design attributes that have been stored in a cloud-based asset manager. So where are we? After 1 year, we've constructed the baseline flow, but our job is nowhere near done. Over the coming phases, we'll be increasingly automating and enhancing this flow, therefore delivering more and more metrics of productivity. We want to make sure security is easy for the designer. Let me spend a bit more time on some of these steps in the ACE flow. At the top of the previous chart, I talked about an IP repository. Let me give you a bit more information about that repository. Well, leading IP vendors like ARM and Synopsys package their design IP with IP-exact metadata, conforming to IEEE 1685, and including important data like, for instance, connectivity information. Our ACE solution further extends and populates that data with additional information about the past characteristics, power, area, speed, and security. The characterized IP is then cataloged in the repository. So now that we have a whole box of building blocks, how do we leverage it? Well, we enable the designer to explore different security architectures. This slide shows 2 of our ACE team members from Synopsys, Amit Garg and Khushbu Mittal. They're in front of a screen view of our ACE Enhanced Platform Architect. On the left, we see a tabular view of a design, and on the right, we see a graphical view, not only of IP blocks, but also those blocks as they've been stitched together. Architectural exploration is depicted in a box on the ACE top-level slide. Introducing security can certainly add chip area and can also impact speed and power. So how much security can I introduce into a design before I exceed my design specs? The benefit with the ACE system is that designers can perform that exploration early at an architectural level with fast exploration and with blocks curated from the IP repository. So for example, suppose a designer wants to include a crypto accelerator IP block, and it needs to be resilient. So they'll start off with 128-bit logic locking as a security mitigation. But if the design needs even more resilience, that designer may evaluate increasing it to 256-bit logic locking and may also introduce obfuscation. At each step, the designer can quickly and easily evaluate the effect that increased security may have on his or her design. He or she can essentially understand the cost of security strategy and can make early trade-offs before committing to an implementation, thereby, really fleshing out the security requirements early on. So how is IP selection done during exploration? When I specify power, area, and speed, and security criteria, IP building blocks are pre-selected that operate within the chosen envelope because of that metadata that's stored within the IP. In the browser, I can select from among those curated blocks, and the blocks are then stitched together with assisted stitching. For blocks that require security hardening, I can select from a host of available methods, including watermarking, obfuscation, and logic locking. For those blocks being security hardened, Platform Architect automatically creates scripts for downstream implementation tools. Now let me hand the floor to one of our partners on the ACE team, Dr. Robert Aiken, Fellow at ARM.
ARM is investing in confidential computing as part of its commitment to security leadership. As you heard from Deirdre, the ACE program not only enables SoC designers with limited security experience, but also supports interoperability of ARM IP in a secure SoC. When the ARM security engine IP is selected, the ACE tool flow will automatically generate the security subsystem targeted to the developer's needs. ACE allows ARM to work with Synopsys and other partners to automate delivery and configuration, to deliver to ACE consortium standards, and to enable a broader security ecosystem.
Thank you, Dr. Aiken. We have now just reviewed how IP is cataloged and how you can perform early architectural exploration with our security enhanced system. Now let's move on to implementation. ACE fosters a security ecosystem, which has already started in phase 1. In addition to inclusion of the security engines from Northrop Grumman, Synopsys, and ARM, we enable a rich ecosystem of security mitigations. These can come from a variety of sources and can come in at RTL and at gate level. In Team ACE, those security mitigations come from university partners like Florida Institute of Cybersecurity, Texas A&M, Purdue, UT Dallas, and NYU. The benefit is that this system is extensible and allows for security mitigations to be added over time from a host of sources. Let me give you an example of a security plugin. While logic locking is a promising defense to protect hardware designs from attacks like reverse engineering and supply chain attacks, many attacks have been shown to undermine its security by retrieving those secret keys. So here I'm showing an advanced plugin from the Texas A&M team, but specifically from New York University under the leadership of Dr. Özgür Sinanoglu. Their innovation is around truly random logic locking that makes random decisions in inserting key gates and retaining signal polarities, and a dishonest oracle, where essentially security keys are flushed when the system detects an attack via scan sensing. Without getting into all the details, these defenses provide protection against an untrusted foundry, an untrusted testing facility, or potentially untrusted end users. The benefit for the designer is that they can incorporate complex mitigation like these without having to be an expert themselves in those mitigations. Of course, the DARPA ACE IV&V team, led by Warren Savage, will stress test all of these phase 1 deliverables, including the security plugins, as part of their Red Team evaluation process, and we welcome that phase in the program. On the prior slide, I talked about secure keys. Keeping secure keys secure is a systemic challenge for any security program. So when a block gets hardened for security, there are transformations that produce keys or other secure assets. For example, the challenge and response necessary to retrieve an embedded watermark, or the key required to unlock an IP to restore its correct function. TestMax Manager or Design Compiler NXT, shown on this slide, store these assets into the Secure Assets Container, or SAC. The SAC provides secure storage of security assets generating during this design phase. These assets may be later queried to verify that the security transformation maintains correct functionality. For example, our formality tool might need to unlock a locked IP to check its proper behavior. At tape-out, gate-level implementations and the security assets stored in the SAC are promoted to the AMI, or Assets Management Infrastructure, for secure cloud-based storage until they're needed again for provisioning on the factory floor. This process keeps the secret assets secret and keeps them from being disclosed during fabrication. By the way, the Asset Management Infrastructure is developed by IBM, who are members on the Northrop Grumman team. You know, I can't possibly cover all the accomplishments of ACE during this short talk. Year 1 was a big year. Looking ahead, it's going to be even bigger. We have many things to do in ACE, further automating the flow, further delivering on metrics of designer productivity, and adding more and more security functionality and more choice. The result will be an extensible system that enables designers to explore, configure, and implement secure designs, greatly expanding the ability of design teams to design in security. But the real result will be more security-fortified hardware in our defense systems. In today's world, hardware security isn't just a requirement for the warfighter, for space applications, and for our critical infrastructure. It's a requirement in cars, in automated factories, in medical devices, in enterprise IT, and in consumer devices. As our team delivers on ACE, and as we transition the technology to commercial and US government deployment, this future is going to be realized. I'm truly excited about what's ahead on the program and looking forward to Phase 2. Thank you all so much for your interest in ACE. Now we have 2 other Synopsys presentations at this ERI Summit. Dale Donchin will give an update on our ACE emulation project that's part of POSH, also under Team Surge, and Dr. Ming Zhang will share his perspectives on the emerging world of 3D ICs. Thank you so much for your time and attention today.
Presenting the Sith Cyber-Physical Automotive Demonstration, DARPA MTO Program Manager, Mr. Keith Ribello, and Dr. Daniel Zimmerman, Principal Researcher at Galwa.
Hi, I'm Keith Ribello. I'm going to talk to you today about the System Security Integration through Hardware and Firmware program. To get things started, let's watch this video.
In our hyper-connected world, we have a flood of information at our fingertips. But that connectivity has a downside, the constant threat of cyber attacks. At DARPA, we recognize the gravity of this modern existential threat, which is why we developed the Sith, System Security Integration through Hardware and Firmware program. Discover how we're utilizing new technologies to stop intruders and keep systems safe. Millions of devices are vulnerable to cyber attacks every day, and we do what we can to protect them. But updating our software and password protocols never seems to be enough. The result? Data breaches, security exploits, and billions of dollars a year lost to cybercrimes. That's why DARPA is developing a better way. For over 60 years, DARPA has held to a singular and enduring mission to make pivotal investments in breakthrough technologies for national security. With that, we identified a problem plaguing the electronic systems we rely on to defend the nation. Current efforts to protect them rely on patches to the software layer, without addressing critical underlying vulnerabilities. Imagine eliminating those vulnerabilities and the peace of mind you feel when you know your system is safe. That's why Sith goes beyond software patching to address the security vulnerabilities at a whole new level, the hardware level. That's our vision for the future, hardware-based security that can detect and prevent attacks, closing off entire classes of vulnerabilities exploited through software. Electronic systems are everywhere, running numerous aspects of our daily lives. The modern car is one example of that. Virtually all of the functionality relies on a system of computing devices, sensors, and other electronic components. And just like all systems, those electronics can be compromised. Our demonstrator was built to show how a car is vulnerable to cyber attacks and how Sith can help. Here's how it works. This car's system is about to be exploited through an over-the-air update. As you can see, the intrusion will use a buffer overflow attack to overwrite the signing key. As a network request containing malicious code is input into the program, it is written into a part of the computer's memory called the stack, overflowing into adjacent areas of the stack and corrupting their contents. This corruption transfers control to the malicious code, which overwrites a key stored elsewhere in memory. Now, with the key replaced, the attacker can upload their own malicious firmware to completely take control of the system's operation. This allows the attacker to send corrupted messages that can affect the car's critical systems, which can result in dangerous situations. The Sith researchers are exploring a number of different design solutions to deflect these types of attacks. Here are two unique design approaches. The Hardware Architecture Resilience by Design, or HARD approach, uses a multi-pronged hardware solution to protect against multiple classes of vulnerabilities. Rather than perform major surgery on the main CPU pipeline, it adds a set of pipelines running in parallel to the primary CPU execution pathway. This acts as a parallel security coprocessor, monitoring the main CPU and standing ready to flag any malicious operations. So when network requests attempt to overrun the boundaries of the target memory space, it senses the nature of the data in a particular pipeline is out of context. Based on the nature of its function, the coprocessor can take a number of actions. In this case, halting the compromised process and keeping the system safe. Cherry, Capability Hardware Enhanced RISC Instructions, was designed to extend conventional hardware instruction set architectures with new architectural features, enabling fine-grained memory protection and highly scalable software compartmentalization. In this example, message types that are specific to the brake controller containing malicious data are transmitted from the infotainment unit over the entire CAN bus, where they are recognized by the brake controller and read into the ECU, which is running a program with a buffer overflow vulnerability. But when the vulnerable program attempts to write the overflow data in the CAN message to the memory space, the program lacks the permission or capabilities required by the hardware. So the malicious code is never completely written into the stack, and the system remains uncompromised. Via hardware-based architectures and associated tools like these, we can safeguard systems against various classes of hardware vulnerabilities. Through an array of hardware-based checks and barriers, Sith stops hacks by detecting a malicious memory access behavior before it is able to overwrite the signing key. So when a malicious message attempts to exploit a weakness in the code, it causes a permission violation that is detected by Sith, preventing the attack before any damage can be done. This revolutionary approach can transform how system security is done, protecting government agencies from outside attacks, securing corporate enterprises from hackers, and helping consumers keep their personal data safe. With the Sith program, DARPA is already breaking the cycle of data exploitation by developing hardware security architectures and associated design tools. Our demonstrator car is making virtual stops at events throughout 2021 to introduce the Sith concept to the cybersecurity community, share in their experience, and see how we're utilizing new technologies to keep systems safe. Join DARPA in our system security integration and start driving toward a more secure future with Sith.
Sith's security goal is to mitigate 7 classes of weaknesses defined by MITRE's common weakness enumeration. In the video, we saw an example of weakness in the buffer errors category. Other categories addressed by the program include injection, resource management errors, privileges, permissions, and access control errors, numeric errors, information leakage, and hardware or system-on-chip implementation errors. For this technology to be used, we know that it can't impose too much overhead on processor operation. The program's goals were to limit performance overhead to less than 10%, power overhead to less than 5%, and processor area overhead to less than 30%. We also want the techniques to be scalable to different classes of processors. We defined 3 baseline target processors for the program, ranging from the P1, which is a 32-bit processor with no memory management unit, representing low-power microcontrollers, up to P3, which is a high-performance 64-bit superscalar processor with a memory management unit and out-of-order execution. All of this contributes to the overall Sith goal of making secure processes that are really usable. One of the challenges of the Sith program was measuring the security improvement that the processors provide. Sith used 3 testing approaches to do this. The first approach was the development of an automated testing architecture to dispatch diversified security test cases to prototype secure processors emulated on FPGA development boards. This provided a continuous evaluation capability during the course of the program. The second approach was DARPA's first crowdsourced bug bounty program called Finding Exploits to Thwart Tampering, or FET, which we ran during the summer of 2020. During the 3-month-long event, more than 580 security researchers attacked prototype Sith processors hosted on FPGAs in the Amazon AWS cloud. Those processors ran software stacks based on FreeRTOS, Debian Linux, and FreeBSD that included disclosed software vulnerabilities that were known to be exploitable on conventional processors. FET showed that the Sith processors were very effective in stopping real-world attacks against these vulnerable software stacks. And finally, we have engaged in external partners for detailed evaluations of the Sith architectures. A report published by the Microsoft Security Response Center in 2020 analyzed the ability of Cherry, one of the Sith architectures, to mitigate vulnerabilities reported to MSRC in 2019. At the time of the evaluation, MSRC found that Cherry would have deterministically mitigated 31% of the analyzed vulnerabilities, meaning that these vulnerabilities would not have required a software patch on systems using Cherry. The number was estimated to rise to 67% if using Cherry features that were still under development at the time of the report. In the final phase of Sith, additional external evaluation partners have been engaged to test the processor's limits. All of these evaluation approaches give us confidence that Sith security protections really work. We've also built multiple demonstration platforms to show that Sith is usable and can protect real-world systems. FET showed the ability of Sith processors to execute multiple operating systems, protecting networked applications from attack. In the final phase of Sith, we have developed an automotive demonstrator to show the process and benefits of integrating Sith secure processors into a cyber-physical system. This is representative of the embedded systems that operate some of our most critical infrastructure. Dan Zimmerman from Galois will now give you a detailed description of the automotive demonstrator. Dan?
I'm Dan Zimmerman, and I'm going to talk about the Sith Cyber-Physical Demonstrator. The Bespin team that developed the Sith Cyber-Physical Demonstrator also includes Joe Canary, Rami Tadros, Michael Podrasky, and Ethan Liu at Galois, Stephen Osborne and Chris Dobelstein, the staff at Kaya who made the look of the demonstrator come to life, and several others. First, a little background about Galois. We were started almost 22 years ago by faculty at the Oregon Graduate Institute to apply functional programming techniques and formal methods to the problem of information assurance. We now have about 130 employees at 3 offices in Portland, Arlington, and Dayton. We work mainly for government clients, doing R&D in several areas related to high-assurance computing systems, like programming languages, binary analysis, formal verification, security, and cryptography. We use lots of different tools and techniques, including symbolic execution, model checking, interactive theorem proving, and automated solving, and we often develop custom tools in-house as part of our projects. We open source our work wherever we can. That includes our core formal verification tools like Cryptol and SAW, and also the entire infrastructure we've developed around our Sith project, including the security testing infrastructure, the AWS infrastructure we developed for the FET bug bounty, and the cyber-physical demonstrator I'll be talking about here. So, what exactly is the Sith cyber-physical demonstrator? It starts with a compact car, paired with state-of-the-art driving simulation software called BeamNG, with Sith security-enabled processors replacing parts of the car's original computer system, and an interactive interface, which we call the hacker kiosk, that lets you attack various systems in the car while somebody is driving it in simulation. There are also visual cues about the state of the security protections and computation happening in the car, and the whole thing is designed to have the feel of a hands-on museum exhibit, where a driver, a hacker, and observers can all experience it simultaneously. So, why did we decide to demonstrate Sith technology with a car? There are a few reasons. First, a car is universally relatable. Pretty much everybody has either driven a car or ridden in a car at some point, so the experience is familiar. Also, modern cars generally contain many vulnerable networked computers. and a security issue in a car can cause serious, easily understandable consequences. In 2015, Charlie Miller and Chris Velasek demonstrated this pretty dramatically by taking full remote control of a Jeep driving at speed on a crowded freeway. They first messed with the radio, windshield wipers, and climate control, and later cut the transmission entirely, forcing the vehicle to stop in an active traffic lane. The driver in that case was a journalist expecting the hack to occur. But Miller and Velasek didn't need the driver's cooperation to execute it. They could have done it on any other Jeep of the same model that they could find on the cellular network that day. Another reason for choosing a car to demonstrate Sith is that it creates an engaging, immersive experience. As the driver, you get to feel the road vibrations in your seat and the steering wheel, and directly experience the effects of hacking. The loss of control can be serious, like when your brakes and throttle are disabled or your steering goes crazy, or less serious, like when you just can't stop the infotainment system from playing dubstep at full volume. And as the hacker, you get to experience the power of having an immediate, visible, and audible effect on the driver, as they crash into a tree, plummet over a cliff into the ocean, or just scream in frustration at your music choices. A third reason for demonstrating Sith with a car is that it makes Sith explainable to a wide variety of audiences. Non-technical audiences can see and hear the difference between the car in regular operating conditions, being hacked, and being protected by Sith, both by visual cues on the demonstrator, like colored lights to indicate hacking or protected mode, and by actually watching and listening to what happens to the driver on the road. Technical audiences can see more detail, shown in explanatory text and imagery, about how the hacks work against the unprotected car, what the Sith security protections are actually doing, and how Sith stops the hacking attempts. And finally, demonstrating Sith in this setting gave us the opportunity to incorporate multiple Sith technologies in the same demonstrator. The SRI Cambridge and Lockheed Martin Sith teams have developed very different protection mechanisms for their processors. Our model of the car's computing system has two levels, one for the infotainment system and over-the-air update functionality, and another for the ECUs controlling the car's critical functions like acceleration, braking, and steering. So we can use one team's processor for each level. You've already seen a bit of the demonstrator in action, and I'll show more about how the interaction between the hacker and driver works for the individual hacks later on. But first, let's talk about how we built it. We started with two compact cars, one to make the actual demonstrator, and the other to use for parts and to reverse engineer components in the lab. The car shown here is actually one of them. We took one of the cars and stripped it down to the frame, removing almost everything: the engine, transmission, all the fluids and glass, the seats, although we did put one of those back later, the roof, the doors, and more. We then attached a commercial force feedback system, the black box at the right of this image, to the steering wheel linkage with some custom machined parts, which you can see in the center. This way, the steering wheel still controls the actual front wheels of the car, has a realistic feel, and can actively work against the driver when an attack on the steering system takes place. We also added 2021 individually controlled LEDs to the car, arranged to highlight individual car systems and show the status of the car with respect to hacking and Sith protection. And finally, we added LCD screens for the windshield and the infotainment system for the driver, and the hacker kiosk and a live display of CAN messages at the back of the car. We also added mounting hardware for the Fpga boards that host the Sith processors running the car's systems. Meanwhile, in the lab, we reverse engineered the communications of the instrument cluster and the shifter so that we could integrate them into the demonstrator and allow the driver to have a working dashboard. Even the hazard lights work. We implemented a CAN bus over Ethernet and put the Fpga boards on it to let Sith processors handle the infotainment system and control the throttle, braking, shifting, and lane-keeping assist functions. There are 6 Fpga boards in the demonstrator, 2 for a baseline unprotected mode, 2 for a mode where Sith protects only the infotainment system, and 2 for a mode where Sith protects only the critical systems. Because the Sith processors only run at very modest speeds on Fpga, somewhere in the 100 MHz range, this lets us keep them all up and running and switch between scenarios quickly, rather than waiting for them to reinitialize every time. There are 2 different levels of hacking in the demonstrator. There's a hack of the infotainment system's over-the-air update functionality, which allows the hacker to get a foothold in the car and also to affect non-driving systems like music and the GPS. And then from there are several different hacks of the car's critical systems that each affect a particular driving system, like the brakes or the throttle. Both levels of hacking take advantage of a lack of memory protection in the unprotected CPUs of the car. Let's take a look at the car hacks in action. On the left, you can see the car from various angles, which will let us examine the effects of all the hacks on both the driving simulation and the demonstrator lighting. On the right, you can see the display that's on the hacker kiosk. The person playing the hacker role starts by going through some informational screens that tell them about the demonstrator and the mechanics of what's going to happen with the hacks. Initially, that a weakness in the car's over-the-air update functionality is going to allow them to replace a firmware signing key and then upload their own malicious firmware. They start the exploit, and when it completes, they have full control of the infotainment system. They can retrieve the car's GPS coordinates, change the music station, change the volume, and prevent the driver from changing them back, as you can see. Next, they can launch hacks of the car's critical systems. Using the infotainment system as a jumping-off point, they send corrupted messages on the CAN bus to exploit weaknesses in the car's ECUs. First, they attack the accelerator ECU, causing the throttle to stick at 100%. As you can see, this results in the driver hurtling into a tree despite her best efforts to stop the car. Next, they attack the brakes, removing the driver's ability to activate them. The red lights on the front wheels indicate the successful hack, and once again, the driver crashes the car. Next, they attack the transmission, forcing it into neutral and removing the driver's ability to shift gears. The lighting inside the car changes to red, and the car slows down. Finally, they attack the lane-keeping assist system. This convinces the car that lane-keeping assist cameras are installed when they're not, so the system processes garbage data instead of real sensor data. This causes the steering wheel to move uncontrollably, leading to a crash. Once they've successfully executed all the hacks against the unprotected system, it's time to try against the Sith processors. However, all the infotainment hacks fail when the infotainment system is protected by Sith. Similarly, all the ECU hacks fail when the infotainment system is left unprotected and only the critical systems of the car are protected by Sith. Let's go into a little bit more detail about the protection mechanisms that defeat the different hacks. The infotainment system is protected by Lockheed Martin's HARD processor. HARD monitors the instruction stream for specific patterns that are indicative of security violations. When one is detected, HARD triggers an interrupt to make the OS kernel kill the offending process. The infotainment system hack takes advantage of a buffer overflow vulnerability in the car's over-the-air update service to run exploit code that overwrites an update signing key. After making a specially crafted request to the over-the-air update service, any malicious firmware update will be accepted as authentic. Once HARD detects that the instruction sequence handling the request has overflowed a stack buffer, it triggers an interrupt to kill the over-the-air update process before the hack can be completed. This results in a small amount of downtime for over-the-air updates, since the update process has to be restarted, but that's far better than a compromised infotainment system. The critical systems of the car are protected by SRI Cambridge's Cherry processor. Cherry adds hardware support for capabilities, which provide a mechanism for both memory protection and scalable software compartmentalization. The Cherry hardware detects when software exceeds its assigned capabilities and terminates its execution. The critical systems hacks use the foothold gained in the infotainment hack to broadcast badly formatted CAN bus messages. These contain exploit code that overwrites important parts of ECU memory, taking advantage of a weakness in the ECU's CAN bus message processing. When Cherry detects the unauthorized memory write attempts that result from the badly formatted messages, it prevents them from executing, and restarts only the offending software compartment. That allows the system to recover quickly, and doesn't affect driving performance at all. So, what's the end result of this? We have a cyber-physical demonstrator in the form of a car that can be used to communicate both why Sith hardware protections are important and how they work to a wide variety of audiences. And the fact that it's something so relatable to so many people shows the broad impact that Sith can have, not just on technology in the defense sector, but also for a wide range of civilian applications. Thank you very much for your attention.
Welcoming back DARPA MTO Program Manager, Mr. Keith Rebello.
Earlier today, you heard about our system security integration through hardware and firmware, or Sith program. We are in our final phase, and we have two different performer architectures working. Our capability hardware enhanced RISC instructions, or Cherry architecture, replaces pointers with capabilities to provide strong memory protection and compartmentalization. It works well for general-purpose computing environments where code can be recompiled to take full advantage of the Cherry instructions. Hardware architecture resilience by design, or HARD, makes use of parallel security pipelines to monitor the intent of the instructions being executed. Since no changes to the main pipelines are done, there are no impacts to performance and no recompilation is required for protection. This works particularly well in embedded applications where it is known what is executing on the system. Both approaches have been extensively tested and integrated into multiple applications, like the automobile you saw. To date, we have been emulating our RISC-V designs in FPGAs, but we are now taking the technology to the next level. Many of you have been asking for this, and I am happy to announce that we are moving from RISC-V to ARM and building silicon for both capability-based Cherry and context sensing hard. The first effort I want to talk with you about is the Morello program. We're working with the UK Research and Innovation Agency to build a high-performance quad-core processor using our Sith Cherry architecture. ARM, the University of Cambridge, Microsoft, Google, and a host of other organizations have partnered to produce a complete development system. In addition to the hardware shown here, a full software stack modified to fully exploit the Cherry security approach is in development. The design is already taped out, and DARPA is looking to make some of these development boards available to interested parties in the ERI community for testing and evaluation next year. We at DARPA are taking the lead in developing a processor for embedded applications. Over the next 2 years, Lockheed Martin will develop a dual-core ARM system-on-chip ASIC incorporating hard security pipelines and DIB-requested peripheral interfaces. Our goal is to be compatible with the OSD SHIP advanced packaging ecosystem to make insertion to DoD applications as painless as possible. This device will be available for testing and evaluation in 2023. After successfully demonstrating the Sith approach using the RISC-V architecture, DARPA has turned its attention to ARM, with two contrasting approaches coming available by a limited number of development boards over the next couple of years. We are looking for evaluation partners with real-world use cases and well-defined transition pathways to commercial and defense applications. You can contact us with questions, to request more information, or to express interest in participating in an ARM-based evaluation project by contacting me or emailing us at sith@darpa.mil.
This concludes our morning presentations. Join us in the exhibit hall to view posters and demos. Parallel workshops will begin at 3:15 p.m.